Okay folks, let's have a look at matrix or linear algebra. Very, very big section in mathematics and quite an exciting section as well. My name is Dr. Jacques du Plessis and I work at the University of the Witwatersrand in Johannesburg. Okay, let's see what we talk about when we talk about matrices. The first question that comes to mind is, what is a matrix? Well, a matrix is an array of numbers or symbols. Okay, there's important language here. It is an array of numbers or symbols or expressions that we organize in rows and columns. That is what we call a matrix. Okay, so an example of that would be if I remove myself from there we go. An example of that would be the matrix that looks like this. It has 3 rows and it has 3 columns. So if it's arranged in that order or arranged like that, we call it a matrix. It is an array of numbers or objects or whatever we want to talk about, arranged in rows and columns. Okay, so if I now want to see more or know more about that matrix, I can talk about the size or the dimension of the matrix. Well, if it has 3 rows and 3 columns, then we have a matrix that is 3 by 3. So the dimensions is represented by the rows and columns. Now folks, in that order, we don't put the columns and then the rows second in another representation of the matrix. We keep it the same. We stick to the convention, which is rows first, yeah? The rows comes first and then the columns after that. Okay, so that matrix up there is a 3 by 3 matrix, since it has 3 rows and 3 columns. But now because it is 3 by 3, it has the same number of rows and the same number of columns, we call it a square matrix. Okay, so if you ever hear anybody refer to a square matrix, you immediately know the number of rows and the number of columns in that matrix are identical. Okay, so what do we use a matrix for? Well, there's quite a lot of applications for matrices. Before matrices were invented or discovered or whatever you want to say it was, it took quite long to solve problems. Okay, and when matrix theory was introduced, it made the time that it takes you to solve something rather quick. So they used for plotting graphs. There we can plot graphs with them. We use them in statistics or economics, and also we do scientific studies and research in a large variety of fields that use matrix algebra to do that. Okay, so matrices are also used in representation of the real world then. Data like population numbers, the infant mortality rates. Recently we can think about the way the COVID virus is spreading around the world, can be modeled using matrix algebra. Okay, so it has an endless amount of applications. The matrices, by the way, is the plural for a matrix. Okay, they are also used in basic algebraic processes, which could be complicated to solve without the matrix. Now just think about it. If you solve 2 equations, algebraic equations in 2 variables x and y simultaneously, it can go quick. You can do it by substitution or you can do it by elimination. Well, when you have a 3 by 3 system, so an XYZ system, it still can be solved paper and pencil, but it's going to take you twice the amount of time that it took you to solve a 2 variable system. Now just imagine having an equation in 20 variables. You have 20 equations, 20 variables. It'll take you some time to solve it with paper and pencil solutions like you've learned earlier. Well, the matrix is there to make it rather quicker for us to do just that. Okay, so let's look at the terminology and the basic principles about matrices. First of all, the dimensions, the rows and then the columns. That is standard, folks. We always do that. So if we look at that matrix, it has 3 rows, 2 columns. So it's a 3 by 2 matrix. The next one has 2 rows and 2 columns. It doesn't look like it because of the fractions, but each fraction represents an entry. So it's a square 2 by 2 matrix. If we look at that matrix, it's called a column matrix. It only has 1 column and multiple of rows. Any column matrix, that one particularly is three rows. Remember, the rows come first, yeah? Remember, our rows comes first and then our columns. So that matrix up there is represented as a 3 by 1 matrix. There's 3 rows, 1 column. Now a row matrix, and that's why we call it a column matrix. So a row matrix has 1 row and multiple columns. That particular one has 1 row and 3 columns, so it's a 1 by 3 matrix. Okay, and here in general, if we look at this notation, the rows are represented as horizontal entries, columns as vertical. But what is important now is we need to talk about the element of the matrix. So if we look at the number 3, the number 3 lies in row 2, and column 1. Okay, so in general, that will then be the entry. If this name of the matrix was A, that will be the entry 2 and 2. It's the second row, the second column. In general, we refer to it as Aij, where I represents the number of rows and J represents the number of columns. Okay. So types of matrices. What types of matrices are there? Well, there's a row matrix and there's a column matrix. We've spoken about those. Diagonal matrix is something new. Well, a diagonal matrix, if you look at the matrix, it has only non-zero entries on its diagonal. Everything else in this matrix have zeros. So we say a diagonal matrix is a matrix in which entries on the outside of the main diagonal are 0. The term refers to square matrices only. Okay, we can only have square diagonal matrices. Okay, so just again, a diagonal matrix, all the entries that are not on the main diagonal in that matrix are zeros. Okay, a zero matrix or a null matrix. A zero matrix or a null matrix is a matrix of all entries being 0, as you can see over there. Then we have a zero or a null matrix. Okay, an identity matrix is something else. An identity matrix is a matrix here with entries on its diagonal. Remember, the previous one had the same. The diagonal matrix had entries on its main diagonal, everything else is naught. Now the same happens in your identity matrix, but all the entries on the diagonal is a 1. Everything that does not lie on the main diagonal is an entry of 0. Okay, so it also then applies to a square matrix. All matrices that are identity matrices are square matrices. Now look at this particular one, the scalar matrix. Now, how is that different from the previous one that we looked at, where we had an A, a B, and a C? Okay, let's see. It's different in the sense that all the entries, there's not an A, a B, and a C there. There are entries that are not 1 and that are the same on that main diagonal of the matrix. So we call that type of matrix a scalar matrix. More theoretically, it is basically a square matrix, which it is, whose all off-diagonal elements are 0, like for the other 2 matrices we've looked at, but all on-diagonal elements are the same. They equal to each other. So in that sense, the identity matrix, yes, could be called a scalar matrix, but the identity matrix has a particular purpose, so we will stick to its name, as an identity matrix. An identity matrix has all the elements on the main diagonal being being 1, the same, and they are 1. Okay, so we're still looking at the types of matrices, and we're looking now at what we talk about when we talk about a triangular matrix. It's a special kind of matrix which is going to become very important in our future calculations with matrices. So the upper triangular matrix refers to the matrix, the matrix is called upper triangle if all the entries below the main diagonal is 0. So everything above, you can see here, everything above the main diagonal there are non-zero entries over there. Okay, but below the main diagonal you have zeros. It's almost counterintuitive to call it upper triangular, because one would like to think of it as the zeros determining its name, but it isn't really like that. It's the other way around. So remember, if I say upper triangle, the zeros are below the main diagonal in the matrix. So if we get an upper triangular one, we should get a lower triangular one, and you've guessed it, all the entries above the main diagonal are indeed 0 entries. Okay, so the triangular matrices obviously have to be square matrices because their diagonals become very important here. Okay, so let's have a look at some more terminology about and basic principles about matrices. The elements in a matrix, we referred to that earlier. The elements or entries in a matrix are named generally by referring to their position. Now remember, what did I say? I say rows and then columns. Okay, so that here, by calling it A, there's a meaning to that. There's a meaning to that 1 and a meaning to the 2. So let's see what it means. The 2 means that the column number of that entry is 2. So that's one of the entries in column 2. Which specific entry are we talking about? Well, the entry in row 1, column 2. So it lies in the first row in the second column of the matrix A. So that A refers to the name of the matrix. We're going to call matrix A, matrix B, matrix C. We might multiply them together, we might add them together. We do operations with them like we do operations on numbers. Okay, so there is your elements of your matrix. So if I have an M by N matrix, then the elements on my diagonal is indicated by the rows and columns being the same. All elements that start with a 1 there, folks, are elements in the first row. All elements that ends with a 2, lies in column 2. And all of this belongs to the matrix A, because the name of this matrix is matrix A. So A21 is the entry in row 2 and column 1 for matrix A. Okay, in general we write Aij, again a reminder, I is the row number and J is the column number of each particular entry. Okay, so let's look at an example. What can we say about the following matrix? Well, let's see. That's definitely not a square matrix because the number of rows is 3, the number of columns is 4. Okay, so there's no diagonal in this matrix. So the matrix B can be described as a 3 by 4 matrix, defined by its size or its dimensions. 3 rows, 4 columns. Well, if I want to talk about the entry 9, I'm going to call it B1, 3. First the row, then the column. So that is entry B1, 3. Okay, let's have a look. First of all, it's a 3 by 4 matrix. It's not a square matrix. The matrix is known as matrix B and B2, 3, 2, row 2, column 3, where they intersect is where we can find this entry. B2, 3 as entry number 8. Okay, so let's talk about matrix equality. Okay, to understand matrix algebra, folks, it's very important that you understand what we say when we say two matrices are equal to each other. So two matrices are equal if all three of the following conditions are met. There's three conditions that we need to focus on. The first one is each matrix must have the same number of rows. Okay, very important. Each matrix must have the same number of columns. Now, if they have the same number of rows, the same number of columns, what else is there left to do? There's the entries that we need to look at. So that's the third condition. The corresponding elements for each of the matrices has to be identical. So if row 1 column 2 in the first matrix has a 3 in it, then row 1 column 2 in the second matrix must have a 3 in it as well. Okay, so let's look at an application. Consider the three matrices there. Which of those matrices have the possibility of being equal to one another? Well, the same number of rows, 1, 2 rows across, same number of columns, 2 columns, 2 columns, 3 columns. So C can never be said to be equal to A and B, because the number of columns is not the same, the number of rows are the same. So if I now say A is equal to B, very important, that's how we write it. It will only be equal if A is equal to B. Well, there's a P here, that P has to be 7. This Q, which is the variable in matrix A, has to be -3 for those two to be equal to one another. And as we said, C cannot equal A or B since it has 2 rows and 3 columns. Okay, so that concludes our discussion of the elementary language, the language we use when we talk about matrix algebra and about matrices itself. Okay, so I hope that helped you. If you like the video, folks, please press the like, subscribe to the channel, and share this video.